Hello? Okay, so hello everyone. So, so the goal of this paper is to improve the understanding of Scala. And Scala was first released in 2004. Meanwhile, its formalization began around the same time, but its soundness proof only appeared in 2016, and there are more versions since then. But the question is, how do type soundness proofs help to implement the compiler directly? So in particular, the calculus being sound doesn't mean the implementation is correct if it just does something in the ballpark. So in this paper, we consider the decidability of a defining feature of Scala called path-dependent types. And the theoretic result also benefits the implementation. So let's look at some example. So here I'm showing a trait, or actually two traits. One trait called account. A trait in Scala is like an interface in Java, so pretty much the same thing. So and then I'm defining another trait called bank. So it has a type member called A, which is required to be a subtype of account. You can also create an account with initial balance, and you can transfer money from one account to another, potentially in a different bank. So if we look at the signature of this transfer function, the last parameter has the type to bank.a, which depends on a previous parameter, which has type bank. So in general, in Scala, we allow types to depend on previous parameters, and type of such form are called path-dependent types. So let's look at some running programs. So here I'm repeating the signature again, and I'm defining two banks, Bank of Waterloo and McGill Bank, and then I'm creating two accounts. So I'm creating David from Waterloo and Ellie from McGill. And then let's take a look at this program. So this program tries to transfer $10 from David to Ellie. And if we check the types, if we do the type checking by hand, so we will see this program is going to compile and actually do the money transfer. Okay, but what about this program? So on the second line, so I just change McGill Bank to Bank of Waterloo. So this program, well, it's not going to work because the program, the compiler is going to find out, okay, Ellie has type McGill Bank.a, and actually Waterloo.a is expected. So the idea of using path-dependent types here is to enforce the compiler to check the association between bank and account correctly during compilation. So as we can see, path-dependent types are very expressive. Okay, but it's not that obvious how should the type checking to be done, or even more fundamentally, is type checking decidable with path-dependent types? And even before answering that question, we have to understand whether subtyping is decidable to begin with. So in order to study this problem, we need a calculus to work on, and Dsub is our calculus. So here I'm showing three rules. The top and the bottom rules say that the top type and the bottom type are the extrema of this subtyping, and the referral rule says the subtyping relation is reflexive. The BND rule compares two type declarations. So a type declaration stores two types, the lower bound S and upper bound U. And when we compare the lower bounds, we compare them contravariantly. The OR rule compares two dependent function types. So when we compare the parameter types, we compare them contravariantly. And before comparing the return types, we push S2 into the context before comparing. So this treatment allows return types to depend on X, which makes the function dependent. So the cell rules specify how we should use path-dependent types. So for a path-dependent type X.A, in cell 1 prime rule, it essentially checks that X can be typed to a type declaration with lower bound S. And if that is the case, then we can extract S and make it a subtype of X.A. And dually, in cell 2 prime rule, if you find U to be an upper bound of the type declaration, then we can extract U and make it a supertype of X.A. And then we have the trans rule, which imposes transitivity on the subtyping relation. So it might appear to some audience that the calculus looks moderate, so probably the undecidability proof should be fairly straightforward, but the actual proof is quite tricky. So for example, the trans rule just doesn't provide strong enough inductive hypothesis. So in order to actually establish the proof first, in the first step, we need to find a suitable undecidable problem to reduce from. And secondly, we need to define another alternative definition of Dsub called Dsub normal form by restricting the trans rule. And then we have to show that these two definitions of Dsub are essentially equivalent. And then we conclude undecidability of Dsub via Dsub normal form. So let's take a look at the first step. So there is a previous attempt that tried to prove this undecidability. So in their approach, they essentially defined a translation function which maps types from F sub to D sub, and they also show a direction from F sub to D sub as indicated by the double arrow above. So however, they didn't show the other direction, which goes from D sub to F sub. And it might look intuitive that this ought to be true, but well, it's not the case because essentially in their translation function, they have these characteristics of mapping both function types and universal types into dependent function types. So pretty much when we prove so that this translation allows interference from the F sub universe inside of a D sub universe, and this interference allow us to construct a counterexample in the other direction. And we actually show a concrete counterexample in our paper. So if you are interested, please take a look at our paper. So instead, so that means we are not able to reduce from F sub. Instead, we do a very simple treatment. So we just directly remove function types from F sub, and we created another calculus called F sub minus. And the consequence is definitely if function types doesn't exist, then also the case in the translation function also is gone. And then also the direction from F sub minus to D sub also would work, but we are not very sure about the other direction at this moment yet. But what's pleasant is that subtyping of F sub minus remains undecidable. So in our second step, we're trying to restrict the trans rule. So the trans rule appears to have a very tight relation with this very unexpected phenomenon. So let's see. So here we assume X is bound to a type declaration with S being lower bound and U being upper bound. So in that case, we can use cell 1 prime rule to extract the lower bound and make it a subtype of X dot A. And we can also use cell 2 prime rule to extract U and make it a supertype of X dot A. And then by transitivity, we managed to prove that S being a subtype of U for any S and U. Well, in general, in Dsub, type declarations can reflect bounds into subtyping relation. So the intuition is that when you say, oh, I have an interval from S to U, you're pretty much implying S is smaller than U. So, and this phenomenon, we call it subtyping reflection or bad bounds in previous literature, but we really like this name of subtyping reflection. So if we collapse the phenomenon into a rule, we obtain a rule that captures the phenomenon which is presented here. And we replace the trans rule with this rule, and the resulting calculus is called Dsub normal form. So now we have two definitions of Dsub. So in our third step, we want to examine what's the properties or what's the relations between these two definitions of Dsub. So first, we show that Dsub normal form admits transitivity. So now transitivity is not an axiom or it's not a rule in the definition, but a provable property. And then we are able to show that subtyping in the original Dsub and in Dsub normal form is actually equivalent. So the theorem here, we have mechanized all the theorems here, so you don't have to take my speech for granted. If you are interested, please go ahead and take a look at our artifact. So here now the diagram has changed a bit. So instead of directly going between f sub minus and d sub, we kind of sneak a d sub normal form in between, and we've already shown the equivalence, and then I claim that the direction going from f sub minus to d sub normal form remains easy. So what about the other direction? Well, it turns out subtyping in d sub normal form is undecidable. So the very special capability that the SR group brought us is that it provides strong enough inductive hypothesis which allow us to finish this theorem. And then, due to the equivalence, we managed to prove Dsub subtyping is actually undecidable. So here is a bit of my thought about Dsub. So since we used to call subtyping reflection bad bounds, right? So we consider the phenomenon is something bad, but we actually want the calculus or the subtyping relation to be transitive. So transitivity is actually something good. But in Dsub, right, as we just show, because of the equivalence, subtyping reflection and transitivity are essentially the same property. So they are actually two sides of the same coin. Whether it's good or bad actually depends on which angle you look at it from. But the nice thing of capturing subtyping reflection is that it inspires us to a very straightforward study of decidable fragments. So next, let's take a look at, so in our paper, we discussed two decidable fragments. So here, the first decidable fragment is kernel Dsub. So, so it kind of resembles kernel F sub. So the first, so here I'm showing two rules from Dsub normal form. The R rule compares dependent function types, and the SR rule that captures subtyping reflection. So the first treatment that we're going to do is we're going to just completely remove the rule capturing subtyping reflection. The reason why we do that is first, this phenomenon is unexpected. And secondly, the Scala compiler doesn't even try to implement this rule, so it's technically correct just to remove this rule. And the second treatment that we're going to do is we are requiring the parameter types of this. When we compare dependent function types, we require them to be identical. So this treatment resembles a kernel F sub. That's why we have this name of kernel Dsub. So, and this modification suffice to define kernel Dsub. So here, this theorem says that kernel Dsub is decidable. It ensures our intuition of that these treatments indeed bring us decidability, and the decision procedure is an algorithm called step subtyping, previously existed and designed by Nieto. But one problem of kernel Dsub inherited from kernel F sub is that it requires when it compares to dependent function types, it requires the parameter types to be syntactically identical. So for example, this judgment is going to be rejected by kernel Dsub because if you look at the parameter types, x.a and top, they're just not going to be the same. But, well, if we look at the context, x is bound to a type declaration with both bounds to be top, and in this very special situation, we call x.a an alias for top. So what that means is kernel Dsub pretty much prevents us from using type aliasing interchangeably, and this is not something that we would expect to happen. So we actually want to leave this limitation. So the undecidability proof actually indicates a very the reason for this undecidability is because of the subtyping rule to compare dependent function types is biased towards the dependent function type on the right. So there's some asymmetry going on here. So if the problem is asymmetry, then the solution is to recover the symmetry just by operating on two contexts. So here I'm showing, so on the right, here is the new judgment. So in the old judgment, we say in gamma, S is a subtype of U. So on the right, instead, we just change the association. We say S in gamma 1 is a subtype of U in gamma 2. Wow, that change of interpretation gives us, so it implies that a type only concerns the context on its side. So here, the SK-SAL2 rule is responsible for extracting the upper bound. But if you look at the rule carefully, when it looks up X, when it looks up X, it only looks up X in gamma 1. In particular, the status of X in gamma 2 is unspecified. And it might be bound to something, some type. It might be bound to the same type or not, or it might not even in the domain. And the second treatment that we do is that to completely symmetrize the OR rule. So now, as you can see, the parameter types, they don't even have any syntactic relation as long as S2 is a subtype of S1. And what's more, here, before we compare the return types, the U's, we push S1 and S2 into their respective contexts. So therefore, we recover the symmetry. So this theorem confirms our intuition, and it says that strong kernel Dsub is decidable, and the decision procedure is an algorithm called subtyping, which we define in the paper. So here, let's go back to the example that we had before, which is rejected by kernel Dsub due to the parameter type being not syntactically the same. So now we are able to compare the parameter types, and it's kind of obvious because because top is literally a lower bound of x.a. So we actually managed to omit this judgment in strong kernel Dsub. So therefore, we have this theorem saying strong kernel Dsub is strictly stronger than kernel Dsub. So here is the summary. So it turns out the four kinds of calculus, the four kinds of calculi that we investigated actually appear to line up very beautifully on an axis of expressive power. So kernel Dsub being the least expressive, and then strong kernel Dsub, and then this kernel, and then this Dsub without subtyping reflection, which I didn't talk about in this talk. And then the most expressive ones are the full Dsub and Dsub normal form, which are equivalent. And we can even further draw a vertical line in between to distinguish the decidable and the undecidable. So I hope our work interests two different groups of audience. So for theorists, we present a very systematic way of investigating decidability. And for practitioners, we develop an algorithm, a concrete algorithm that is proven correct. And furthermore, if people create a GitHub issue complaining about why Scala has no transitivity, well, now we have a paper as a justification. That's it.
Thank you. Questions? Okay, so the difference between kernel Dsub and strong kernel Dsub was this all rule having the more symmetric case?
Yes.
If you change...
Well, so pretty much in strong kernel, we operate on two contexts like consistently.
Yeah, so if you changed Dsub to also use two contexts, would it be equivalent?
No, it's not going, well, unless you change Dsub to have S2 over here, then it's kind of redundant, right?
So it wouldn't change...
If you change S1 to S2, right, then it would have been the same as Dsub.
Okay, yeah, that's...
Yeah, so the creativity is over here, so we kind of weaken the comparison, but still it's kind of stronger than kernel Dsub.
Okay, thank you.
Yeah.
Another question? Do you have one? Yeah, can you read it, please?
What about other features of Scala? Can you talk about it?
So here this paper pretty much focused on introducing the methodologies. But actually, it's actually this work is part of my thesis, part of my master's thesis. So in thesis, I extended this method to, for example, intersection type. It would work, actually, including the undecidability results. And but I'm not sure about like mu types, because mu types has other problems that I wasn't able to tackle. But indeed, like I mean, this methodology can go quite a bit far.
So what's really implemented in Scala? You said that Scala doesn't implement the transitivity rule.
There's no transitivity in Scala.
Oh, okay.
Yeah, and yeah, somebody complained about it on GitHub a couple years ago, but it was a bit of hand wavy. But
let's ignore it. Okay, so since this was a distinguished paper, I have certificates for you.
Thank you. Thank you.
And thank you.